right here, the small one that's green. There, you can use half of it to know that because it's facing this way, that this is going to be twice the amount over here. So if we know the measure of CD, then we know that this angle A over here, or angle CAD, is going to be half of what CD was. Or vice versa, if we know angle CAD, then we know that we can multiply it by 2 to get the angle measure of CD. And in the next picture below it, it describes that chords, which are from on the inside of the circle and go from one point to another, but they have line segments. That measure, in this example, measure AED right there in the blue. This is going to be half of what BC was, so it's this. Also, you can use in this picture too, with chords or secant lines, either one. This says that AE times EC in this picture over here. So we have line AE multiplied by EC. Right there, that is a chord, is equal to the same distance that DE times EB is going to be. So if you take this part of this line and this part of this line and you multiply it together, it's going to be the same as if you multiplied this together and this part of this line together. And in the next example, if you take this part, BC, and you multiply it by the length of this whole entire thing, AC, it's going to be the same as on the other side, where if you multiply CD by EC, the whole entire thing, it's going to be the exact same. And that is because you have these measurements here, and then you have they're intersecting at the exact same point. So that's why they're going to be equal to each other. And this is the formula. This is part of a formula you can use, which is they use the tangent AB here, and if you square it, then it would be equal to the length of BC times EB, this whole entire length right over there. These are more examples of some problems with exact numbers. So in this one, we're given EC, DE, BE, but we don't know the length of AE. So that's what we're trying to figure out. So we get 4x for multiplying AE times EC to get 4x is equal to, if you multiply BE by DE to get 8 times 3. And 8 times 3 is 24, so 4x equals 24. If you multiply both sides by 4 to get x alone, then x equals 6. So now we know that AE is equal to 6 units. Over here, it looks a little bit more complicated, but it's not. So you multiply x is the unknown that we don't know, which is EC, and then we have x plus 10, which is multiplied by. So we take, it's basically just like proportions or the ratios. So you have a small amount right here that you're trying to figure out from this large amount when we know kind of the same proportions on the other side. So you multiply this small proportion over here, DE, which is equal to 3, multiplied by the whole entire length, which is 3 plus 5, over there. And that is where this first equation would come from. So then, solving it out, you have x times x is x squared plus 10x over there, is equal to 24. So then you take that information and you can subtract 24 over here and put it on this side, and then that way it's easy to factor out. You can get your two possibilities, because it could be positive or negative, but we know that it's going to be positive because you can't have negative amounts of units in degrees or radians in the circle, because you're not going backwards. So then you get x plus 12 multiplied by x minus 2 when all of this is factored out. And then we know that x could be a possibility of negative 12 or x equals 2, and we know that it is x equals 2 automatically because this is the number that does not have the negative in it. Over here we do not know what AB is, and so that's what we're trying to figure out. So we take x squared over here is equal to 2 times 18. We get 18 from these over here, and you multiply the 2 by that. Multiply this by that to get this. So then we know that x equals 6 from solving that out, and it can't be negative. This is a proof based on quadrilaterals with circles. So we're given that BC and CD are tangent lines to circle A, and we need to prove that BC is equal to CD. Well, we know from what we've already learned that that's true, but we have to explain it. So the explanation is that we have to start off with our given, and our given is found up here, is that BC and CD are tangent to circle A. So we already know that information. And then based on what we know, we can figure out from there is that angle BC right here and angle DC are right angles. And this is because of the tangent lines. We always know from the radius to the tangent line that it's always going to be a 90-degree angle. So that is our reason right there. From that, we can figure out that line AB and AD are similar or the same because there are the radii from the exact same circle of circle A. And so anywhere you go around the circle, that length is always going to be the same. And AC is equal to AC. So this side of this triangle and this side of this triangle are going to be the exact same due to the reflexive property. And so then we know if that is similar, then we can see what other pieces of this triangle we can make similar. So we know that triangle ABC is going to be equal to triangle ADC based on the hypotenuse leg, because we have two right angles and we are able to make this side, side AC, congruent due to the reflexive property. So then we can figure out this last, that BC and DC are equal of the two triangles because of congruent parts of congruent triangles are always congruent, or CP, CTC, which I forget what that stands for. Here's another example here. We have the given information. This is more like a flow proof, is that AC, which is the radius of circle A, and we also are given that measure BEA is equal to 90 degrees. We're trying to prove that BE and ED are similar. So we start with what we're given, and then we know the definition of a radius, so we are able to then prove that they are radii of A, and that would make them similar because they're of the exact same circle, so AB and AD would be similar. And then AE and AE would be equal again because of the radius, and then parts of the triangle are congruent because you have this part of the triangle and that part of the triangle, and that's equal.